So let's start dependency parsing. And we all know that it is really important for many applications. And a good book to start with is Dependency Parsing written by these guys. And Nivre is pioneer, and McDonald they are pioneers in this area. But we don't talk about dependency grammar. We only talk about dependency parsing, which is slightly different. And it has huge applications: machine translation, information extraction, co-reference resolution. This is really interesting. Text summarization, question answering. So there are three major approaches for dependency parsing. Transition base is really fast, order of n of complexity, very fast. But it has its shortcomings because, if the sentence is too long, it cannot capture all of these dependencies very much. So you just use it for very short sentences. On the other hand, graph-based approaches are great. They can handle very complex, very long sentences, but the order of complexity is too big. We don't like it. So we want to improve it. So if you want to write an article, please improve the computational complexity of this graph-based approach. Maybe combining the paradigms of 1 and 2, maybe combining the paradigms of 2 and 3. But here in this playlist, I just ignore the third approach, which is grammar-based, because I believe that the first and second approach are good enough to handle our problems in chatbots, voice bots, in any application, in banks, or in like Siri, Alexa, and those things. So we don't need the third approach. But it's my opinion. And what is the dependency structure? Nodes correspond to words, and labeled arcs correspond to type dependency relations. I'm sure you're already familiar with these things. For example, everything has a root. The verb, for example, had is the root, and so everything could have a subject, object. So any two words, there is a relation between them, and it has a label. And so this is a phase structure. The information encoded in a dependency structure is different from the information captured in a phase structure. So we are not talking about phase structure, although it's really important in computational linguistics, but for slightly different purposes. So I just want to talk about dependency parsing. So here is a list of more common criteria that have been proposed for identifying a syntactic relation between a head and dependent. A head and dependent. A head and dependence. So this is a head for another dependence. So it always depends on the direction of this edge. So there are some rules we should care about. H is obligatory, D may be optional. You see, D is just cares about those detailed things that when we talk about heads, when we care about the big picture, we try to see the nodes that are very close to the root of the tree. Because the other nodes are just the details. For example, when we want to answer a question, we don't care about the details. First, we want to know what is the global picture. What is the global essence of that question or that sentence? What is the essence of that? We don't care about the details of implementation of that or something that is details. So we can define the parsing problem as data mapping an input sentence consisting of words W0, W1, Wn to its dependency graph. So for each sentence, we have a dependency graph. For sentence 1, we have dependency graph G1. For sentence 2, we have dependency graph G2. By the way, among all graphs for sentence 1, only G1 is the optimum. It is the gold. It is the optimum. The other one are less probable. They are not important. So an approach is data-driven, that I really like, if it makes essential use of machine learning from linguistic data in order to parse new sentences. An approach is grammar-based if it relies on a formal grammar. But how do you deal with that with things like Sanskrit? So that's why the first and second approach, which are transition and graph-based approaches, are much more tractable, much more popular, much more beautiful. So we want to use supervised dependency parsing. Assume we have a rich language like English, that we have lots of training data, lots of trees for lots of sentences. So we first learn it. Given a training data, induce a parsing model M that can be used to parse new sentences. After learning, you don't need to do it again. You use the already ways of the learning. You go to inference directly. And the inference is parsing. So given a parsing model M and a sentence S, derive the optimal dependency graph for S according to M. So this is a dependency graph and a trees. So this is a directed graph. It's not undirected. So the direction is important. So we have some nodes and some relations. And because in directed graphs, we call it arcs. So A is arc, V is nodes, the nodes in this. For example, a sentence, we have economic news had little effect on financial markets. So we tokenize it, so it has economic, and we always add this root at the beginning of any sentence. So we tokenize it, economic news, so we make them apart, and then, so as you see, our arcs are pairwise words. For example, had news has a relation subject between them. Had effect has a relation object between them. Attribute and different relations. A dependency tree always satisfies spanning property over the words, and that's why these spanning trees, minimum spanning trees, those things that are in classical computer science, and I've explained about them, and I've explained them in my playlist for approximation algorithm, graph theory, large graphs. You can watch my playlist and appreciate the beauty of these spanning trees, which are very useful in computer science. And now we are connecting machine learning, which is modern problems of computer science, to very classical NP-hard problems and those computational complexity problems of classical computer science that goes to 100 years ago. And many of them are introduced by, for example, Hungarian mathematicians such as Erdős and those things. So we are connecting those traditional things to our machine learning problems of 2022. So you see that all topics in computer science that I've talked in my YouTube channel are related to each other. So they are not divided. Everything, you should have a holistic view of all of the topics. Otherwise, you cannot create new paradigms. Otherwise, you cannot appreciate the beauty of computer science. So the projective dependency tree is when you can't cross the edges. For example, this is projective dependency. It is a dependency tree, and first of all, we should define what is projective. It is projective if and only if omega I has a relation to omega k. But I mean, most of the time, it is not projective, and it is non-projective because these edges cross. So non-projective dependency tree, a projective dependency tree satisfies the planar property. It's a planar graph. You see, I cannot cross these edges. For example, I cannot cross this one to another node. I cannot do this because it is planar, so it's just a planar property. Planar graph. I have explained it in my YouTube channel, so you can think about that. So it's a very restrictive subclass of graphs. And a dependency parsing model consists of a set of constraints, gamma, that define the space of permissible dependency structures. So what are these constraints? The constraints are specific to the underlying formalism used by a system. Minimally, the constraint set maps an arbitrary sentence and dependency type R to the set of well-formed dependency graphs. And this is important. Additionally, gamma could encode more complex mechanisms, such as context-free grammar or constrained dependency grammar that further limit the space of dependency graphs. So in each paradigm, such as transition-based, graph-based, grammar-based, what do I mean? By constraint is different. We have different constraints. So the learning phase is that we have a set of sentences and corresponding dependency trees. We want to learn that and then infer that at the test time. So the learning phase of a parser aims to construct the parameter set. We want to learn this and to data-driven systems. The parameters are learned using a training set consists of pairs of sentences and their corresponding dependency trees. So most likely dependency tree, the function h, is search over the set of all dependency graphs. And we do it by some neural network, by some classification methods in the transition-based method. And so methods for finding h is greedy, like the transition-based, it is greedy. It could be recursive, like those dynamic programming approaches. Of course, in graph-based is a little bit recursive, and the based on chart parsing techniques. And I really like this Persian poet. Life is a balance of holding on and letting go. For example, you stick on one NLP subject, but you have temptation to learn different paradigms. So you should let it go and see the big picture. You should see different algorithm of NLP. You should not focus on just one approach. You should see different approaches. So what you seek is seeking you. The quieter you become, the more you are able to hear.